Hello everyone, I am Yash Patel, a second year student from IIT Roorkee from branch Data Science and Artificial Intelligence. Today I'm going to present a presentation on the topic the four fundamental subspaces and their application. So let's start. Okay, so what we will cover in this presentation is basically what are the four fundamental subspaces, how to calculate them, their application in different problems, some real life problems, some real world problems, and finally the how to find them, code in Python. So some prerequisites which may help to understand this better are the basic understanding of linear dependence and independence, which in short I can explain. For checking it, basically we can check if a non-zero solution for alpha, beta, and other all the constants exist, then the solution basically the vectors are independent. Otherwise, they are dependent. Uh, Vector space. The second prerequisite is vector spaces and subspaces. Their knowledge, like for vector spaces, in short, we can say that it must follow the addition property and the multiplication one. Which is basically if V belongs to a subspace is belongs to a space, say S, and vector U belongs to a space S, then V plus U must also belongs to the same space. And if V belongs to space S, then lambda times V must also belongs to space S. So that is the basic requirement for a set of vectors to follow to be in a vector space. Now, ideas about the basis and dimension of a matrix, which is basically, say a matrix is given. So its basis and dimensions are basically the basis is basically the minimum number for a space, the minimum number of vectors which are required to span the whole subspace. So it is minimum. I have enough of them, but not too many. We can understand this by like that. And the basic idea of linear algebra. Okay. Now, what are the four fundamental subspaces? Four fundamental subspaces of matrix A. So it is basically the row space, column space, null space, and the null space of A transpose, which we say as left null space, also known as. So coming to the first one, the row space. Row space is the subspace spanned by the rows of a matrix. It represents all possible linear combination of the rows. We can understand this by a example. So let us say a matrix A is given. So here it basically consists of two rows. So its row space will be all the combination of these making the rows, assuming one row as a vector. So its all combination will be a row space, of the given matrix. So here the same thing I have written where alpha and mu are constants, scalar constant. Okay. So we can see that here says the number of columns is 2. The matrix have two columns. So the each element of the space here we have chosen has two, 6 4 2. So the row space will be a subspace of R2 because the number of columns is 2. Okay. R2 has basically all possible subspaces of R2 can be, it can be like only the null vector or any line passing through the origin, or it may be the whole plane. Okay. So since in our case, both the rows are independent to each other. Okay. So it will span the whole XY region. Whole XY region. Because both the vectors are independent to each other. That are the 3, 1 and 6, 4. Okay. Uh, Now, how can we use this? So it is used to check the consistency of a consistency of a system. Okay. So let us say a system AX is equals to B is given. Okay. So for checking its consistency, we can use the row space. How I'll tell it. It is also used to determine rank of a matrix. So what is rank of a matrix? Say a matrix is given. So convert it into upper triangular matrix. That is, all the lower elements will be 0. All will be 0. And the diagonal elements will be any constant. Okay. So this is known as the echelon form of a matrix. So after converting into echelon form, if we count all the pivot elements are basically the non-zero first element in the row. Okay. So the number of all that columns which have pivot elements not equals to 0, that will be our basically the rank of a matrix. That is the number of non-zero rows of a matrix after converting it into a echelon form. So once we find the row space, so its dimension will be the rank of that matrix, and which will further tell about the consistency, that whether the solution for this will exist or not exist. We can check this further. So how will the rank tell about consistency? We can check from here. Say a matrix A M cross N is given. Okay. So 4 possible cases are there. In first case, here M is number of rows and it is number of columns. In first case, say rank is equals to number of rows is equals to column. In that case, for sure and sure, only one solution will exist. So we can say that the system is consistent. And after converting it into the row reduced echelon form, it will look something like this. Here I is the identity matrix. Means, say if it is 2 cross 2, then it will be something like this. 3 cross 3, then identity for that one. It is basically its row reduced echelon form. In second case, let us say that the rank is equals to number of columns but is less than number of rows. In that case, 0 or 1 solution may exist. So we cannot say that the system will be consistent always. It may happen that the system is inconsistent, but it may also possible that it is consistent with one solution. In that case, the row reduced echelon form will look like this. In third case, say rank is equals to number of row but less than number of column. In that case, infinite solution will exist and system will be for sure consistent. Here basically the F is the matrix comprising its all elements as 1. Its all elements will be 1. Okay. So say for one order, or it may be like this. Okay. In fourth case, let us say the rank is less than number of rows. In that case, 0 or infinite solution will exist. So it may be consistent or inconsistent. Both may happen. And the row reduced echelon form will look something like this. Okay. So coming to our second subspace space, which is column space. So similar to row space, column space is the all possible combination of its columns. Okay. So for a matrix A, here since there are 2 rows, 2 columns, so its column space will be the linear combination of its column, which is here again alpha and mu are constants, in a constant. Now, what we have seen earlier, by the same way, since here number of rows are 2, so each will have 2 elements, and so the column space will be a subspace of R2, similar to what we have seen here. Three possible cases are possible, and since both the columns are independent to each other, so again in this case, this column space will span the whole xy plane, Now it's coming to its application. Say a given system of equation is Ax is equals to b. So, and we want to see whether the system is consistent or not. So we can check this by writing it this form. Now we can also write this as this: x times the first column plus y times the second column. We can also generalize this for a general vector. So it will be basically first variable times its first column, then second variable times its second column, and similarly. And here the RHS is same as that. So if we want to find out whether the solution is consistent or not, so it's basically from here we can see that it is basically the column space of this matrix, and here it is B matrix, the RHS one. So the solution will only exist if this left hand side part spans this B. Matlab B is in this space which we span in the left hand side. So this is a very strong conclusion, because we can check the consistency. The solution will only exist when matrix B is in column space of matrix A. Okay. The second application is dimension of column space gives ranks of A, which we have seen same in the case of row space. The basis of column space is basically number of columns of pivot columns of A. Okay. And fourth is it helps determining the range of linear transformation, because basically since we have seen this, so all the it's all these combinations are basically what it may vary from its whole range. Now coming to third and most important subspace, which is null space. Null space is set of all vector that maps to the zero vector under a linear transformation. It means that say a matrix A is equals to 0. So all the set of vector which transform this a linear transformation to matrix A, which transform this to a null vector. So all those vectors comprises of the null space. Okay. So it is basically the solution of homogeneous system of linear equation, that is Ax is equals to 0. So its solution will be the null space. One question may arise that why the solution of Ax is equals to 0 will be a space. Means it can be a set of vectors which is not a space. So let us check that why it will always be a space. So let us assume that X contains two vectors u and v. Then Ax is equals to 0 and X contains two vectors v and u. So if we put v here, then we will get AV is equals to 0, and by putting u here, we will get AU is equals to 0. Now once we put u plus v here, so we will get AU plus v is equals to AU plus v, and which we can expand it further like AU plus AV. And earlier we have seen that from here we can see that AU and AV are 0. So AU plus V is also 0, which proves the additive property which we have seen in the starting part of the slide. Okay, now the second property, and for the multiplication one, since AV is equals to 0, we multiply both sides by the lambda, where here lambda is a scalar constant. So we will get A lambda V is equals to 0. And finally, since here 0 into lambda, which is basically 0, so which proves the multiplicative property. So since it satisfies both the properties to be a space, and other the inverse one, multiplicative inverse and additive inverse will also be followed. So we can say that X will always be a subspace. Okay, it will be a space. All the solutions to X is equals to 0. So here all the possible X must be a space. because it satisfies all properties to be in the to be a space. So now coming to how to find a null space of a given matrix. So say a matrix A is equals to of order m cross n is given. So for finding its null space, first convert it into a row echelon form. A row echelon form which we have seen, the upper triangular matrix. Now find its rank. From here we can find its rank by counting the number of pivot elements. Now we define a term free variable q, which is equals to n, which is number of columns minus the rank. A is m cross n. Here n is number of column, and rank we get from above. So we can get number of free variables. Now what we need to do is find q unique solution and all their linear combinations. Say q, it comes, we get, say q comes out to be 2, so we have to find 2 unique solution, and all their linear combination will basically give us the whole null space. That will be the null space. That is the algorithm for finding null space. So what are its application? If a homogeneous system of equation is given, then its solution is basically the null space of the matrix, which we have seen earlier also. We can extend the same logic, in fact, for the system which is non-homogeneous. So say a metric system of equation Ax equals to b is given. So in this case, if we need to find out x, so this will be basically xp plus xn, where xn is the null space, okay, and xp is the particular are all the particular solutions, and xn is the null space. Now coming to fourth space, which is the left null space. The left null space is the orthogonal complement of column space. It consists of vectors that are orthogonal to all columns of a matrix. So it is basically the solution to A transpose y is equals to 0. So here this y is known as the left null space. Okay. We can visualize it from here also. So say this is the our row space which comes out to be this space. So the null space will be perpendicular to row space on orthogonal. The dimension of it row space will be rank, which we have seen earlier, and so the null space will perpendicular to this, and similarly column space will be perpendicular to left null space. Okay. Now let us take an example for seeing how we can find the null space. So let us take a matrix A is equals to 1, 2, 6, 2, 6, 8, and 2, 8, 10. So for finding its null space, we have to find the null space of this matrix. So first, our first step was to convert it into echelon form. So what we can do is just replace R2 by R2 minus 2R1 and R3 by R3 minus 3R1. On performing these operations, we will get our matrix as, it will be basically 1, 0, 0, 2, 0, 0, 2, 2, 2, and 2, 4, 4. Okay. So here our pivot elements. This is our first pivot, second, and okay, and pivot. So from here we can see that rank of this is 2, as number of, we can perform actually a further transformation, that is R3 can be reduced by R3 minus R1 R2. Okay, so we will get the matrix finally as 1, 2, 2, 2, 0, 0, 2, 4, and it will be all zeros. So now this is our echelon form of a matrix. So from here we can see that its rank is equals to 2, since number of non-zeros rows is equals to 2. Okay. And so number of free variables is equals to 4 minus 2, which is equals to 2. So means we need to find two particular solutions. Okay. So for finding particular solutions, we since what does this number of free variables tell? It means that two variables can take free values. So we can decide two variables, and we can find the rest of the variables by solving this system of equation. So let's find the two uh, solutions. So it will be basically, let us take, we can assign any variable to be 0. So once we take x1 is equals to 0, x2 is equals to 0, and in other case we can take similar any other thing. So in my case, I am taking x1 to be -2, x3 to be 0, or we can take the simpler one so that we can easily solve the equation. Say let us take the let us take x3 to be equals to 0 and x4 to be equals to 0. So we will get on solving x1 to be -2 and x3 and x2 to be 1. The other solution I'm taking is x2 is equals to 0 and x4 is equals to 1. So on solving, we will get x1 is equals to 2 and x3 is equals to -2. Okay. So its null space will be basically all the combination of the vectors which we have find. So its null space will be basically alpha times -2, 1, 0, 0 plus beta times 2, 0, -2 and 1. So this is basically the required null space of A. Okay, now coming to next slide. So what are the applications of the row space, column space, and null space, which we have seen earlier? So a very huge example of this is it is used in image compression. Image compression can be done using SVD and PCA. So in SVD, it performs this concept helps a lot. So in image compression, an image is represented as a matrix. Any image is represented as its matrix, and where each element of this matrix basically tells about the pixel values. These are pixel values varying from 0 to 255. Okay, this matrix can be quite large, and thus it may lead to storage problems. So the column space of image matrix consists of all possible linear combination of its column. This column represents the image pixel value, as vector is a high dimensional vector space. Okay, so the column space and SVD are leveraged in image compression by identifying and retaining the most significant components of the image matrix. This reduces the dimensionality of image representation, leading to efficient compression while balancing the trade-off between image quality and compression ratio. What this means is that we can choose the selected columns, which are basically left the other ones. So it will be basically the column space. So here we can use that if we have the better knowledge of the column space. Okay. Now another example is PCA. In image compression, aims to reduce the amount of data required for representation the image while preserving its essential features. Okay. The key insight is that singular values in sigma represent the importance of different components in reconstructing the image. In basically in SVD, we can represent the matrix A as U sigma V transpose. So to compress the image, we can select the top case singular values and their corresponding values from the U and V. U and V are basically this matrix which we get from the SVD. So this column represent the most important patterns of feature in the image, and by selecting fewer values, we can reduce the dimensionality of our image representation, which may help in space storage and all this problem. We can see how PC visualization of it. So it basically calculates the perpendicular distance from all the points and tries to reduce it. Okay. Another example we can see in electrical circuits. So basically null space helps to find the node voltages in circuit with Kirchhoff's law, and left null space is used in solving problems involving transposed circuit matrices, which we can use the null space for finding the voltages. Okay, node voltages. These are just a few examples. There are many huge applications also of these fundamental spaces, which helps us to understanding that how the bigger things work. So it is basic and small thing, but it helps to understand bigger things in better way and how they work internally. Okay, we are taking the example for a third point, the electrical circuit analysis. So let us say a circuit is given as this. So for this, we can write Kirchhoff's law. Here four nodes are given. So let us say that the current going outside will be taken as positive and to a node, and current coming inside is taken as negative. Okay. So for the first node, we can write as y1 plus y4 minus y3 is equals to 0. Since from the Kirchhoff's first law, current can't be accumulated or get out from a node. Okay. For the second node, we can write it as minus y1 plus y5 minus y2 plus y2 is equals to 0. It's positive. Okay. For the fourth node, we can write in similar way minus y4 minus y5 minus y6 is equals to 0. And for the third node, y3 plus y6 minus y2 is equals to 0. So this is all the four equations which we can write in matrix form as variables 1 0 y2 y3 y4 y5 and y6 are 0. This is for the first one. For the second one, we can write in similar way 0 0 1 0. For the third one, 0 0 0 minus 1 and minus 1. And for the fourth equation, it is 0 minus 1 1 0 0 and 1. So this is the matrix representation of these equations. Okay, so these are all the I have given all the basic ideas about the four fundamental subspaces, which may be helpful in various ways. So as I have told earlier that it can help us to understand bigger things which are used in practical life, real life, that how they work from inside. Okay, this is from all from my side. Acha, one last thing is left, that how we find the null space in code for it in Python. So a standard library is present in Python which we can use. So let us say a matrix A is given. So for finding its null space, we can basically directly use a dot null space. We have to import a library in matrix, and from here we can directly find its null space. So in final, we can print to check whether it comes out to be a 0 or not. So it will be 0. It basically implements the same way as I have told earlier. Here the complete algorithm for it. It implements internally the same way, but it's just a standard library which we can use. Okay, thank you.